Hello viewers. So in last short video, we concluded with the analysis of balance section. Now let us try and analyze under reinforced section. Under reinforced section. So for under reinforced section, steel is provided in such a quantity that when the steel on tension side reaches to its yield strain, at that time the extreme compression fibers have their strain value less than ultimate compressive strain of concrete, which is 0.0035. The bending strain distribution diagram looks like this. But this is not the bending strain distribution diagram at failure, because just because the steel has reached yield strain doesn't mean that the beam is going to collapse under flexion. Still, we have some load capacity till this epsilon c reaches to the value of strain equal to 0.0035. So if we go on further loading this beam, a stage would arrive where the extreme compression fibers would reach the strain value of 0.0035. At that time, strain in steel on tension side, however, will be greater than epsilon 1. This will be the position of neutral axis at failure from extreme compression fiber for under reinforced RCC beam section. Just look at the notation that I have given for position of neutral axis. It's no longer XUB because B stands for balance section. It is only XU. Now, how this bending strain distribution diagram, for under reinforced section at failure is different than the bending strain distribution diagram for a balanced section. So for refreshing the earlier concepts, I will draw bending strain distribution diagram at failure if this cross section would have been designed as balance section. So as per the definition of balance section, extreme compression fibers would reach to ultimate strain of concrete in compression simultaneously when the steel reaches its yield strain. So as you can observe, the value of strain in under reinforced section at failure is greater than epsilon y, whereas for balanced section it is equal to epsilon y. Whereas the value of extreme compression fiber strain is same. Therefore, it is evident that if I join these two lines, if I join these 2 points, the neutral axis for balanced section would lie below the neutral axis for under reinforced section of same beam cross-sectional dimensions at failure. Now let us draw bending stress distribution diagram for under reinforced section corresponding to bending strain distribution diagram at failure. So as we have already seen, we will have to calculate where does the strain drop down to 0.002, and we know that location will be 4/7 XU from neutral axis and 3/7 XU from extreme compression fibers. So therefore, in principle, the bending stress distribution diagram qualitatively is going to remain same. Stress corresponding to the strain of 0.0035 is going to be 0.446 FCK till the strain drops to 0.002. This stress is going to remain constant, and then we are going to have parabolic variation. at the level of steel, we are going to have strain value greater than yield strain by elastoplastic idealization of stress strain curve of steel. For any value greater than yield strain up to ultimate strain, we are going to have same value of stress, and that stress is going to be equal to 0.87 Fy, tensile in nature, 0.87 Fy. So if you remember, this bending stress distribution diagram is no different than the bending stress distribution diagram drawn for balance section. Therefore, the expressions for moment of resistance, tensile force and compressive force are not going to change for under reinforced section. Only we will replace XUB by XU. So let me write down the expression for ultimate compressive force or compressive force at failure for under reinforced section. The expression is going to be 0.36 FCK B XU. Mind you, instead of XUB, I am going to write it as XU. The expression for tensile force at failure TU is going to be 0.87 Fy AST. And the expression for moment of resistance of under reinforced section, which will be denoted by only MUR and not by MURB because it is not balanced section. It will be given as either 0.36 FCK B XU or 0.87 FYAST, 0.87 FYAST. So magnitude of either of the forces, we know at equilibrium Cu has to be equal to Tu. So magnitude of one of the forces multiplied by lever arm. Lever arm is going to be D minus 0.42 XU. Mind you, it is not XUB. We cannot replace this XU by KUB times D because KUB is the neutral axis factor evaluated for balance section. So therefore, we are not going to replace this XU by KUB into D. So these are the expressions that hold good for under reinforced section. We have just replaced XUB by XU. Now based on this, let us solve quickly a small problem, small analysis problem. Let us say we have a beam of width 230 mm and effective depth of 500 mm. We have a beam of width 230 mm and effective depth, that is the distance from extreme compression fiber till the centroid of the steel, that distance is given as 500 mm. And let us say this beam is reinforced with 3 bars of 12 mm diameter on tension side. So this beam is subjected to sagging, and let us say it is reinforced with 3 bars. So we denote 3 numbers as 3 hash, 3 bars of 12 mm diameter. So we write it as 12 mm phi. So let us say that this beam is reinforced by 3 bars of 12 mm phi. The grade of concrete that has been used is M20 and grade of steel that has been employed is Fe415. And let us say we need to compute how much external UDL will this beam support if it has a span of 3 meter, simply supported at ends, excluding self weight, excluding self weight. If this beam should not collapse in flexion. So let me repeat the problem statement. A reinforced concrete beam of effective cross section 230 mm by 500 mm. By effective cross section, I mean width is 230 mm and 500 mm is the effective depth and not overall depth. So a reinforced concrete beam of effective cross section 230 mm by 500 mm is reinforced with 3 bars of 12 mm diameter on its tension side. If the grade of concrete and steel employed are M20 and Fe415 respectively, find out the external UDL this beam can support over the simply supported span of 3 meter, excluding its self weight. So we need to compute this W. This should not include the self weight. Now let us try to solve this problem. The first step that we are going to do is, now let us forget about all these strain distribution and stress distribution diagrams. We already have the expressions in place. So let us go to the solution. First step that I am going to do is, let me assume that this beam is under reinforced. I will begin by assuming that the beam is under reinforced. If beam is under reinforced, I know Cu will be equal to 0.36 FCK B into XU. The value of FCK here is 20. Value of B here is 230. Mind you, everything we are substituting in the units of Newton and mm. So this is 20 MPa, that is Newton per mm square. This B is 230, 0.36 is constant, and XU is to be evaluated. Now we can also compute value of TU, which is equal to 0.87 into Fy into AST. So what is the value of Fy? Fy is 415. AST is 3 times pi by 4 into 12 square. 3 numbers, 12 mm diameter bar will have area pi by 4 into 12 square. And we know that Cu has to be equal to Tu for equilibrium. So just observe these two equations. If I equate Cu equal to Tu, the only unknown in the equation is Xu. So I will be able to get position of neutral axis at failure. So let me calculate. So that gives me Xu is equal to 74 mm. Now next step that we are going to do is, we are going to compute the position of neutral axis if this section would have been designed as balanced section. So what is the value of XUB? We know that it is equal to KUB into D. So that is going to be equal to KUB for M20 and Fe415. I'm sorry, KUB for Fe415 is 0.48. Therefore, 0.48 times 500. This value turns out to be 240 mm. Now you can observe XU is less than neutral axis position at failure for balance section. 74 is less than 240 mm, and therefore, as discussed earlier, this section is ought to be under reinforced. We have already discussed by looking at the strain diagrams at failure for balance and under reinforced section that neutral axis for under reinforced section lies at a distance lesser than the distance for balance section from extreme compression fiber. Therefore, this section is ought to be under reinforced. So therefore our assumption is okay. Now, once we know that it is under reinforced section, let me calculate the moment of resistance of this section MUR. This must be equal to either CU or TU. So I will write down 0.36 FCK, that is 20, B, that is 230, XU. Now XU we have already calculated. We have to take that value and not for XU for balance section. So therefore this is 74. 0.36 FCKBXU. This is compressive force into bracket D, that is 500, minus 0.42 into XU. So MUR turns out to be 5746, 5746, 3332, 3332.48. This value is in Newton mm. If I were to convert it into kilonewton meter, I will have to multiply it by 10 power minus 3 to convert from Newton to kilonewton, and another 10 power minus 3 to convert from mm to meter. So total I have to multiply it by 10 power minus 6. So 1, 2, 3, 4, 5, 6. So it is going to be 57.46, 57.46 kilonewton meter. So we have evaluated moment of resistance of this balance section, and that turns out to be 57.46 kilonewton meter. Now let us say the total UDL on the beam, including its self-weight, which I will denote it by WT, causes the bending moment of WT into L square by 8 at midspan. If the beam is subjected to UDL and if it is simply supported beam, we know that the maximum bending moment occurs at midspan, and that value is WL square by 8. So I am not using the notation W, I am using the notation WT. WT stands for W plus self UDL due to self weight. So therefore WT into L square by 8, this can at the most have value equal to 57.46 kilonewton meter. Now, so therefore total UDL including self weight that this beam can support is going to be 57.66, 57.46 multiplied by 8 divided by L square, but L is 9, L is 3, so it is 3 square. So this value is going to be equal to 51 kilonewton per meter. Look at the unit. Unit of UDL is going to be unit of force divided by unit of length. As we have chosen the moment to be substituted in kilonewton meter, length to be substituted in meter, we are going to get this total UDL that this beam can support, including self weight, to be equal to 51 kilonewton per meter. Now let us work out what is the UDL due to self weight. To calculate UDL due to self weight, we will consider 1 meter long chunk of this beam. So cross sectional dimensions are 0.5 multiplied by 0.23. Now we need to be little careful here, as this 500 is given as effective depth. We will have to add this effective cover in order to calculate the overall depth of the cross section. For calculation of self weight, we will require to substitute here the overall depth of the cross section and not effective depth. So for time being, let me assume that this effective cover is 60 mm. Just a random value I am assuming, as the data is not given. But in that case, the total depth is going to be 560 mm. Therefore, it is going to be 0.56. So let me say the volume of 1 meter length of this beam is going to be 0.56 into 0.23 into 1. This multiplied by unit weight of reinforced concrete, which is given in IS 875 part 1 as 25 kilonewton per meter cube. Kilonewton per meter cube. This is the density, weight density of RCC, reinforced concrete. So 25 kilonewton per meter cube into volume of 1 meter length chunk of this beam is going to be this much, and that itself is going to be W due to self weight. It is the intensity of UDL due to self weight per meter run. So we have considered 1 meter run of the beam. So this turns out to be 0.56 into 0.23 into 25. So it turns out to be 3.22. Therefore, ultimate UDL that the beam can carry, excluding self weight, will then be equal to 51.07 minus 1.5 times 3.22. 1.5 is partial safety factor for dead load. So this turns out to be 51.07 minus 1.5 into 3.22. 46.24 kilonewton per meter. Now if I were to calculate the safe intensity of UDL that I can load the beam with, excluding its self weight, that will be equal to this 46.24 divided by 1.5, which is the partial safety factor for load. So that turns out to be 30.82 kilonewton per meter. So this is the answer to the question that we have raised through this problem. Okay. Now we will like to make certain observations. For M20 and Fe415, the problem is over here, solution is over, but we will make certain observations. For grade M20 and Fe415, do we know the value of percentage of tension steel for balance section? The answer is yes. Percentage of steel for balance section with this combination is 0.96. Therefore, tension steel to make this section balance is going to be equal to 0.96 multiplied by 230 into effective depth, that is going to be equal to 500 divided by 100. So what is the steel that you require to make this section balance? It turns out to be 1104 mm square. What is the steel that we have provided or we have been given to be provided in the beam? That is 3 times pi by 4 into 12 square. So that works out to be 339 mm square. So what do we observe? So whenever we are dealing with under reinforced section, we are going to have steel less than the steel corresponding to balance section. So let us summarize few of the observations about under reinforced section. Under reinforced section will have its neutral axis at failure at a level above that corresponding to balance section. That is the first observation. Second observation, area of steel that you provide in the balance section is going to be less than the area of steel that you will provide to make the section as balance. And the third observation, let us now calculate moment of resistance of balance section with this dimension. It is going to be RUB into BD square. So RUB for M20 and Fe415, we know that it is 2.76. We have done this in the last short video, multiplied by 230 into 500 square. This works out to be 158.7 kilonewton meter. I have already converted this into kilonewton meter by multiplying this by 10 power minus 6. So 158.7 kilonewton meter. And what is the moment of resistance of this cross section? It is 57.46. So the third observation, moment of resistance of a balanced section will be less than moment of resistance. The third observation, moment of resistance of under reinforced section will be less than moment of resistance of a balanced section with same dimensions, same grade of steel and same grade of concrete. So there are three ways in which we can show the section to be under reinforced. First way is its neutral axis at failure lies above the neutral axis for balanced section. Second way is its area of steel is less than area of steel corresponding to balanced section. And third, its moment of resistance is less than moment of resistance corresponding to balanced section. So with this discussion, we will conclude today's short video. Thank you.